We've made it to Module 10, Induction and Inductance. So we've studied so far that if we have a current flowing through a wire, and that current produced by an electric field, which is produced by some potential difference, well, that's going to produce a magnetic field. Well, a magnetic field also produces an electric field that then in turn drives a current. When a magnetic field produces an electric field, we say it induces an electric field, or it induces a current, or it induces an EMF. And that's where the induction word comes from. And that's Faraday's law of induction. So observations by Michael Faraday and others also led to this law. And induction is the basic science involved in power, electrical power, electrical generators, and also, very importantly, electric guitars. So in Module 8, we learned if we run a current through a closed conducting loop, it has to be closed or a current won't flow unless it's a closed loop. But if it's flowing through a closed loop in an existing magnetic field, a magnetic field produced by something other than the closed loop, then that magnetic field is going to create a torque to, in fact, turn the loop. So if we have a current loop and we add to that a magnetic field, we get a torque. Well, that's an electric motor. In this module, we ask the question, if we have a loop with no current flowing through it, but it's conductive, or non-conductive we'll look at, but if we have that loop with no current and we turn that loop by hand or some other means, will a current be produced? So we're asking the question, if we have a torque on a loop in an existing magnetic field, will a current be produced? And this is what Faraday studied. So our electric motor, what we've already studied, if we have an existing magnetic field and within that magnetic field we place a current loop and we run a current through that wire, the magnetic field will produce a torque on that loop. Well, if we want it to be a motor, we learn we need to reverse the current every half period, and then we'll produce a continuing rotation. In this question, we're saying if we have a magnetic field and a loop with no current in it, and we try to move it, we're showing rotation with our hands or some other mean, we rotate that loop, a current will then be induced, and we'll be able to measure that current on a little device up here that's called a galvanometer. That's our electric generator, so we know in fact that we have one, because we know there's electric generators. So Faraday's observations, conditions that induce current in a circuit. If we have a magnet and it's brought in motion near a circuit, then a current will be induced. If we have a circuit that's moved in the presence of a stationary magnet or some other stationary magnetic field, a current will be induced. So again, that what's producing that magnetic field could be a magnet or it could be another current carrying loop. But if we move our circuit in the presence of that, we'll induce a current in our circuit. And then thirdly, if we have a current flowing in a neighboring circuit, if it becomes established or disrupted or changes some other way with time, then a current will be induced in our loop, and that will be induced from the neighboring loop, which is the source of the magnetic field. But it seems that something has to be changing. We have to have something moving, or we say some magnetic field is changing with time, being turned on or off, or some other means changing with time. So these two experiments, the first experiment uses a magnet to present a magnetic field in the presence of a conductive loop. The second experiment uses a conductive loop to present a magnetic field in the presence of another conductive loop. So our first experiment, we have a current and induced EMF that appears only if there's a relative motion between the loop and the magnet. If we don't move the magnet, no current. If we move it faster, more current. We'll also see if we move it in opposite directions, we change the direction of the current. And that's what we mean here. If the moving magnet's north pole towards the loop, that causes a current in perhaps the clockwise direction. Then if we turn the magnet around, and turn the south pole in the direction of the loop, that'll cause a current also, but in the opposite direction. And all of this you can see with our PhET labs that we worked with last week. So you can try these out and observe them on your own. So this first experiment using a magnet, if we move the north pole of the magnet towards the loop and it causes a current through in this direction, then that current is then measured on the galvanometer in the positive direction. If we don't move the magnet, then there's no current and no current measured on the galvanometer. If we move if we move the magnet away from the loop, then we still measure a current, but it's in the opposite direction, so it's measured on the galvanometer in the opposite direction. These are the galvanometers we used in earlier labs. If what's not shown here, if we reverse this and we were moving the south pole instead, if this was the south pole that we were moving towards the loop, the difference would be we'd still induce a current, but it would be in the opposite direction. If we move the south pole away from the loop, if this was a south pole and we still moved it away, we'd be inducing a current, but in the opposite direction. So there needs to be movement, whether it's the north or south pole that's moving towards increasing the magnetic field in the presence of the loop or in the cross-sectional area of the loop, or decreasing the magnetic field in the cross-sectional area of the loop. These are all of concern or of interest. The second experiment says a change in current in this right-hand loop will produce an induced current and thus an induced EMF in this left-hand loop. If the current doesn't change with time, no induced current or EMF. So if we did this with a battery, we could close the switch. There'd be no current in this loop. If we close the switch, as soon as we close the switch, we're going to get a current induced in the loop. Let's say we have the current induced in this direction. If we then in turn open the switch, we'll also get an induced current. The induced current will be in the opposite direction. If the current is just left closed and no change in time, then we'll get no current in either direction. So these are the two experiments. So summary of terminology: induced current is a current produced in a loop when there is a change in magnetic field surrounding the loop. We're really interested in the magnetic field that has flux in the cross-sectional area of the loop. And there needs to be a relative motion between the loop and the magnet, or there is a change in current in a neighboring circuit, or there could also be a change in the loop area. So again, referring to the flux through the area of the loop. And we'll look at that. An induced EMF, that's the work done per unit charge to produce that induced current. And induction is in fact the process of producing the induced current and the induced EMF. So Faraday's law of induction, will first express it qualitatively and later express it quantitatively in terms of an EMF and in terms of an electric field. So Faraday's law of induction, an EMF is induced in a loop when the number of magnetic field lines that pass through the loop is changing. This is qualitative in how we can imagine it. The actual number of field lines doesn't matter, but the number of field lines needs to be changing. So there needs to be some change with time, some ddt, either dBdt or a dAdt, and we'll also find we could have a change in angle. So the induced EMF and the induced current are determined by the rate at which those number of lines change. So to put this to work, then, well, let's calculate the number of field lines that pass through the loop. And what is that? That's the magnetic flux. That's analogy to that is the electric flux, which we've studied. There's a very consistent and dual analogy there. We have our closed integral of B dot dA, that's our magnetic flux, our closed integral, surface integral now, of a two-dimensional surface of E dot dA, that was our electric flux. Our dA is the same, it's a vector, it has a magnitude of the area, the differential area, it has a direction that's perpendicular to the loop. So if we pick a section or of the loop or a complete loop that is in one plane, then our area vector is the sum of all those dA vectors. They're all in the same direction. The angle theta here is the angle between the perpendicular to the loop and our perpendicular to whatever this area is, and the magnetic field. So our magnetic flux through the area A is, that what we want to look at is what is the change in that. So we want to know where dA is a vector, the magnitude dA, the direction perpendicular to the loop. If we want to have a flux, a change in flux, so if we want a dflux dt, something that changes with time, then we have a change in the magnitude of the magnetic field, a change in the area of the loop, or a change in this angle, right? That dot product gives us the change in the angle between, because it's our b dot dA is our BA cosine of theta. So if that changes, then we're also going to get a flux that changes with time. So our special case, when our magnetic field is uniform and perpendicular to the plane of the loop, then our closed integral of b dot dA will be our BdA cosine of 0. So it's just going to be our b closed integral of dA. So that's just our BA product, magnetic field times the cross-sectional area of our loop. So here we can get the units. Our units are magnetic field Tesla, area meter squared. So our unit of magnetic flux is a Tesla meter squared, which has a special name of a Weber, named after Mr. Weber, an important scientist. That's why we use a capital W. And it is a unit that actually has two letters, a W and a B, not to be confused with a watt. So that's our introduction to Faraday's law qualitatively. In the next video, we'll look at how to induce an EMF in a loop.